So this is just minus alpha, right? Yes, and alpha is a constant, right? So therefore, I can say that dy equals minus 1 over alpha dt. So I'm going to take this and I'm going to plug it in here. So this equation becomes dp over p equals the mass of a mole divided by r, and then I have an alpha upstairs, no, an alpha downstairs and a dt, right? Is that right? Let me step away and look at it from a distance.
Where did G go?
The G, I lost it here. So the G should be here. Good. That's it. The sign is correct. Right. Good. And now, all of this is a constant. The mass of a mole, G, or alpha, so these are all constants. So now I can integrate both sides. And this is not a bad integral. So the integral on the left-hand side of this equation is an integral with respect to pressure. So my limits of integration, I'll integrate it from the pressure at ground level to the pressure at some height, y. And the integral on the right-hand side is an integral with respect to temperature. So this would be the temperature that matches this pressure, or the temperature at the location where the pressure is P sub 0, and that would be the temperature at ground level. And this is the temperature at the location where the pressure is P. So this is just the natural log of P over P naught, right, when you do that integral. And this is the natural log of T over T naught. So you can write the relationship between them like this. If you don't like the natural logs, you could also do the following, right? You know that the natural log of B equals a natural log of Z, right? This is the same thing as right? So, I mean, you could also express this as P, or the natural log of P over P naught, equals the natural log of T over T naught, raised to that M mole G over, what is it, R alpha? So that P over P naught, then you just compare the arguments, right? Sorry. Yeah, I guess I can write it like this. But I prefer this. And by the way, this has to be like this. So do a numerical problem. What's the pressure, let's say 5 kilometers up in altitude, if the pressure here is 1 atmosphere? If the pressure at sea level is 1 atmosphere, what's the pressure 5 kilometers above? Right. Let me use this one, I prefer that one. So, if the pressure at sea level is, let's say, 1 atm, and the temperature is like today, what do we say, 28 degrees Celsius, that would be 301 Kelvin, right? What else? By the way, we could also do this. You could also write this as the mass of a mole times G over R alpha times the natural log of but what is T? It's, I can use equation number 1. It's T naught minus alpha y. So this, if I use this equation, right, like this part equal to this part, it relates the pressure to the temperature. If I use instead this part equal to that part, then it relates the pressure to the height. Give me the elevation, I'll plug it in there, and then I'll tell you the height. Or you can, use this separately, given the height, and then use this equation over here. So they're all the same. So let's say 28 degrees Celsius, right? Like you said, 80, around 80, 82 degrees. So I think we converted it, we got like 28 or so. So let's just say that, right? What is the mass of a mole for air? Well, H2O, right? So, H2O is water. So we have nitrogen, roughly 80%, and oxygen, which is also atomic, roughly 20%. So the mass of a mole of air would be like, 80% the mass of, nitrogen plus 20% the mass of a mole of oxygen. And so this would be 0.8. Now, nitrogen. Nitrogen is what? What is the total number of nitrogen? And is
the mass is like 14.
7, so 14, right?
It's like 14.0667.
Yeah, so nitrogen has 7 protons, right? So it's got 7 neutrons, so together is 14. So it would be, let's say, 14 grams per mole, right? Plus 0.2. And oxygen has 8 protons and 8 neutrons, so together is 16. Right?
It's like 15.
But then we have 2 of them, right? So it should be 28. And this one should be 32. Because, it's a molecule, not an atom. I mean, most of the mass of an atom is in the nucleus. So, so for nitrogen, N has 7 protons, 7 neutrons, so together is 14. But you got 14 nucleons in one atom, but you have a molecule of 2 atoms of nitrogen, so instead of 14, you use 28. And for oxygen, you have the atomic number is 8, so you have 8 protons, 8 neutrons, so that's 16 for one atom, but you got 2 of them because it's a molecule, so you got 28. But roughly, this is the number that you see at the bottom of the periodic table of the elements. You have, like, if you see oxygen, it'll say something like 7, that's the atomic number. Actually, it'll say 8, not 7. And then it will say something very close to 16. And that number, it's got some decimal places, is in grams per mole. So that's why I'm using grams per mole, grams per mole. Notice that I'm going to be using kilograms, right? So what is this? What is the molar mass of air? You know, treating air as being, you know, roughly with this composition. So we're not going to be so far off if we actually do it, if we just assume it to be just nitrogen and oxygen. So how much do you got over here?
22.4 on the left.
No, it's got to be 28 or something.
Well, no, the total is 28.4.
28.4?
I mean 8. Oops.
28.8?
Yes.
Okay, thank you.
Sorry.
But then we know that 1 kilogram, it's 1,000 grams. So the grams cancel. So this will be 28.8 times 10 to the minus 3 kilograms per mole. That's the, you know, the mass of 1 mole of air. It's roughly 28.8 times 10 to the minus 3 kilograms per mole. So we have that. We have this. And I want to know the pressure in the atmosphere where? 5 kilometers? What if this is 5 kilometers? Right? So let's do the calculation. So, I mean, I could use this here. I just need to find the temperature of the air at a height, at an altitude of 5 kilometers, and then plug it in here, right? So, this is like this, right? So the temperature is what? What did I say? 28 degrees Celsius. Let's do 301 Kelvin instead. Now, alpha is 6. It's a change of 6 degrees for a change in altitude of 1 kilometer, right? So it's 6. It's a change. I mean, I can think of alpha. If I solve for alpha over here, right? What is alpha? It'll be T naught minus T over Y, right? So this is like a delta T over a change in height. So alpha is the change in temperature when you change the altitude by 1 kilometer, right? So because, remember that alpha is 6 degrees Celsius per kilometer, right? Remember that this is a change in temperature of 6 degrees. And a change in temperature in the Celsius scale is the same as a change in temperature in the Kelvin scale. So this is still going to be 6 Kelvin, but per kilometer, right? For 1,000 meters. So this is really 0.006 Kelvin for every meter. So I'm going to use 6. This will be in Kelvin. I'll put in the units so you see that we're consistent for every meter. But then if I want 5 kilometers, that's 5,000 meters, right? So this cancels. I mean, I didn't even have to convert that because this is going to be in Kelvin anyway. So this will be 301 minus, and that would be, is that 30? So what is that? 71? Is that right?
Professor Guerra, referring back to the equation over there, should we use the smaller r? Because isn't the larger r for the number of atoms? And then
No, this r is, I'm going to be using Pascal's. This is 8.214.
Okay. Oh yeah.
It's
Sorry, I was thinking of small n and big N. How? Yeah.
No. Yeah, this is correct, right? Yeah, that's correct. So I could use this equation here, and I say the natural log. This is the pressure that I want. Suppose I wanted it in 1 atm. P naught, I'm gonna use 1 ATM. So my answer is gonna be in ATMs, right? Because that's a ratio anyway. And then I have the mass of a mole of air, which is 28.8 times 10 to the minus 3. And I'll put in the units to show you that one needs to be careful here. This would be kilograms per mole, right? Times G, which is 9.8 meters per second squared. And then R is 8.314. Why can I leave this as 1 ATM over here? Because what I have here is a ratio. I can write this as 1.013 times 10 to the 5th pascals. And that's not going to change this part over here of the calculation. 8.314, and this is what? Pascals, cubic meters, right? PV over NR per mole, I'm sorry, over NT, and this is Kelvin. That's R. And alpha is this guy over here. I'm in meters, 0.006 Kelvin per meter. So notice, this mole cancels this mole. They're both in the denominators, right? So they cancel out. This I have this Kelvin cancels this Kelvin, right? So I have cubic meters over here. This meter is gonna go upstairs to give me meters squared, which will give me meters downstairs, because I have cubic meters in the denominator and meters squared. So I'm gonna cancel this with this and just leave this as meters, right? So we have kilograms, pascals, right? So I'm just trying to make sure that I have the right units here. Pascals times meters. A pascal is a force, right? So that's a force. It's a pressure. It's a force per unit area. So it's a force per unit area, and then this is a distance. Or I'll just call it meters. Right? Now a force is MA. It's kilograms times the acceleration, which is meter per second squared. Area is meter squared, and I have meters over here. So notice that this meter times this meter squared cancels this, and I have kilograms per second squared. So this is the same as kilograms per second squared. I'm still not done because that was only this, right? I have to do the natural log of the two temperatures. And the temperature we said is 271 Kelvin. And at sea level or ground level, the temperature was 301. So these units cancel. And so we get that the natural log of P over P naught, which is 1 ATM if you like, equals. Then I have 28.8, let me just put in the numbers, times 10 to the minus 3, 9.8, 8.314, 0.006, and what do we have left? We have this guy here, pascals times meters, we said is kilograms per second squared. And then we have, notice the units on top, kilograms per second squared, right? So this cancels that. And it should be dimensionless. Times the natural log of 271 over 301. So how much is this? Can I erase this now? I'm going to erase this over here. Let me make myself some room over here. So we have the natural log of P over, let's say, in ATMs. So then we have, how much is this? This is dimensionless.
5.66. You want more on the.
So it's 5.66 and,
It's 5.657.
okay. And then we have the natural log of whatever that ratio is, 271 over 301. So what do you, the natural log of this number is going to be a negative number, because that's less than 1. So when you multiply this will be here on the right hand side. That should be a negative number. What do you get?
Negative 0.1 about.
Negative 0.1?
Or well, for the natural log, sorry.
Negative 0.594.
Like that. So that means that P over 1 ATM is E to the minus 0.594. So P equals 1 ATM times E to the minus 0.594. So how many ATMs is that? So notice, this is 55.2% of an ATM. So 5 kilometers up in altitude, and the pressure there is 55% of what it is at sea level. About half. Any questions? Notice, what if you had written over here, in this natural log over here, what if you had written the natural log of, did we ever calculate the temperature? We said that it was, this is like what, like minus 1 degree Celsius? Is that right?
Minus 2.
Oh, minus 2? 273 is 0, right? So then minus 2, yes. Yes? Suppose you had used, in this part of the calculation over here where you have this ratio, suppose you had used the temperatures in degrees Celsius as opposed to in Kelvin. Then you would have written the temperature of minus 2 degrees Celsius over 28. And you might say, oh, not bad, that Celsius cancel. But you run into a problem over there. You can't take the natural log of a negative number. I mean, use your calculator. The reason why that doesn't work is because to convert from Celsius to Kelvin, you don't multiply it by a multiplicative factor. You have to add, subtract something to it. So it doesn't work. Whereas to convert from ATMs to pascals, you just multiply. So then, and you have a ratio over here. So here, because you have a ratio of this to this, and to convert from one unit to another, you just, it's a multiplicative factor, then you can use the other unit without a problem. But in this ratio involving temperatures, this is the, the temperature at a height of 5 kilometers, and this is the temperature at ground level, right? You don't convert this temperature from degrees Celsius or this temperature from degrees Celsius to Kelvin by multiplying it by a factor so that the factors cancel. Now you have to add or subtract something, so then it doesn't work. So you must use Kelvin over here, not degrees Celsius. And this is the sort of calculation where if I put a problem like this in the test, a lot of people, for example, maybe they'll show how to derive this, but then they'll screw up in the actual calculation of the pressure. And there are two things to pay attention to over here, which is why I'm doing it on the board. One is this. This is a change in temperature of 6 degrees Celsius, but a change in temperature of 6 degrees Celsius is equivalent to a change in temperature in 6 Kelvin. But that's also per kilometer. But if you're going to be using temperatures in Kelvin, you know, the ideal gas law, 8.314 in the metric system, then your distances, your height, should be in meters as well. So that all of a sudden you don't lose a factor of 1,000 that then gives you erroneous results. So anyway, clearly the expression, you know, what I attempted to derive from the very beginning is how does the pressure in the air, and this is not considering windy conditions, this is just still air, right? Essentially what we have is this. So this is, let's say, sea level, this is air, and this is the ocean, right? And at this, you know, temperature is T naught, and the pressure is P naught. If I want to go to this particular depth over here, Y, if I want to know the pressure there, it simply, at that depth, is the pressure at the surface of the liquid plus rho G, Y, where rho is the density of the ocean. Let me call it water here. But if you want to know the pressure here at a height Y, right? And now this is air. Now you have the density of air over here, right? Then the expression is a little bit more complicated. It's the natural log of P over P naught equals, and then you have that factor, the mass of a mole, G, what was it, R alpha, and then the natural log of T over T naught. Now, you want it in terms of Y, right? Just like we have this one in terms of Y. So just replace the temperature here by what the temperature would be at that given height. That would be T naught minus alpha Y. That's the expression to use. Right? Did I leave anything out? So you do this, take the natural log, multiply by that, right? And then E to all of that is going to be